Question 6 then. To save a bit of time, I've plotted the points because 6a is asking me to plot the results given in the table, and you don't want to watch me tediously and painstakingly plotting those. But what I haven't yet done is labelled my axes. And if you are going to plot a graph, you are going to need labelled axes. These bits have been done for us. They have been labelled, but nothing's been marked on them. So strain goes up to 10, so that's pretty straightforward. It's in general a bad plan to choose really awkward numbers when you're deciding what to put on the axis of a graph. Don't go up in threes or something miserable like that. Stress goes up to 3.5, so I think we can do 1.0, 1.5, 2.0, 2.5, 3.0, and 3.5. And that should be fine. And then we really carefully plot all of our points. And in general, mark schemes will suggest that they need to be correct to the nearest minor grid line. So that's okay. Yeah, that does mean that things like 3.15, you don't have to worry about it being exactly halfway in between the 3.1 and the 3.2 line, as long as it's correct to the nearest grid line. So you can round that up to 3.2 and get your marks. Interestingly, there's a typo here. These strains that are giving us 10 to the 3, it should be 10 to the minus 3. Look, imagine what a strain of 10 times 10 to the 3 would be. That's 1,000 times, 10,000 times longer than its original length. It seems awfully unlikely. So 10 to the minus 3 is a much more sensible strain. Yeah, this graph is not yet finished. Obviously, I'd need to do a line of best fit. The draw function on OneNote that I'm using here is miserable for trying to do lines and stuff. So I'm just going to freehand this. You would, of course, use a ruler to draw a line of best fit through the first sort of linear stage, and then it doesn't really matter what happens after that. It is the linear stage that is important in this type of graph because the gradient of that is going to give you the Young modulus. So 3 marks to be had here, and those marks are most likely for the points being plotted correctly, the axes being chosen, the scales being suitably chosen, and for the line of best fit being reasonably well drawn. So I might not get that last mark. Use the graph to find the Young modulus of the metal is 6b. Now, anytime you see this phrase, use your graph, make sure you draw on the graph to make it really, really clear which part of the graph that you have used. I mean, you can just state the points that you've taken, but it is much better to actually draw on the graph. And what the examiner tends to want to see is a really big sort of triangle that you're going to take a gradient from with delta x, delta y written on it, something like that. Make it nice and clear. So this is the point of interest. I'm going from 0, 0 to this point. What is that point? That is 2.4, a strain of 2.4. So delta x equals 2.4 times 10 to the minus 3. And delta y here, it starts from 0 and goes up to 2.5. Delta y equals 2.5 times 10 to the 8. So the Young's modulus is equal to the gradient delta y over delta x, and divide one by the other to get some sort of sensible answer. Always worth bearing in mind when you're calculating a Young modulus that for metals, Young moduli tend to be of the order of 10 to the 11. So if you've got an answer in that sort of ballpark, you're doing okay generally. If you've got an answer that's wildly different from that, you should be very suspicious of that answer. So 2.5 over 2.4, I don't know what that is. I'm going to throw that in a calculator. Let's have a look. 1.04, so I've got 1.04 times 10 to the 11 pascals, and that feels about right. So 6 part C, 3 meter length steel rod is going to be used in the construction of a bridge, the tension will be this, and the rod must extend by no more than 1 millimeter. Calculate the minimum cross-sectional area required for the rod, and we're given the Young's modulus here. So it's a 3 meter length. The equation that is useful to us, Young's modulus equals stress over strain. A quick rearrange tells us that stress therefore is equal to strain multiplied by Young's modulus. We can substitute in, if we wish, force over area for stress equals strain times Young's modulus, and therefore cross-sectional area, which is what we're trying to find, is equal to force over strain times Young's modulus. So in this example, that force is 10 kilonewtons, 10 times 10 to the 3. The strain, 1 millimeter. Remember, strain is extension over length. We've got to be a little bit careful here. The 1 millimeter is 10 to the minus 3 meters divided by the original length, which is 3, and multiplied by the Young modulus of 1.9 times 10 to the 11. So that is the calculation that I'm going to throw into the calculator right now, and we'll see what we get from that. So the calculator has given me 1.6 times 10 to the minus 4, and that seems reasonable. That's in square meters. As a cross-sectional area in square meters, that feels okay. If you think of what that would be, that's about 1.6 square centimeters, isn't it? So that's a reasonably chunky steel rod, and I'm happy enough with that answer. Okay, that is question 6 done, and in fact that is the Quark assessment done.